In this talk, I'm going to introduce an idea that has been developing recently in the field of optics, but that is seeing increasing use in radio frequency electromagnetism, and may be just as useful there. This idea is a different way of looking at waves and electromagnetic fields, one that is economical, practical, and quite fundamental. This different modal approach appears in two related forms: what we can call communications modes, which clarify for us the best spatial channels for communications and allows us to count them. And secondly, what we can call mode converter basis sets, giving us a way of looking at scattering that in one sense is fundamentally optimal, complete, and economical. We are used to modes for resonators and for propagating modes in waveguides. We like modes because they are economical. We can use a few mode amplitudes, not fields at every point, and we can often count modes meaningfully. Modes have very useful mathematical properties, for example, orthogonality and completeness. And we can give a definition of a mode. A mode is an eigenfunction of an eigenproblem describing a physical system. But when we look generally at communicating with waves, or scatterers or optical devices or nanostructures between some source and receiving volume, we need a different kind of mode that looks at these source or input spaces and receiving or output spaces. They are modes in two spaces, not one space. They are not the beams between the spaces. To set up the mathematics of this problem, we consider two spaces. First of all, a source or input volume or space. And this space can contain the possible source functions, and we'll write these using a Dirac notation for convenience, as I've shown here for this function psi s. Similarly, we will have a receiving or output volume Vr, which will contain the possible wave functions, and again we will write those functions using a Dirac notation for convenience, here phi r. The sources in the input space give waves in the receiving space through some coupling operator, which we'll call GSR here. For free space, this would be based on a free space Green's function, such as a scalar monochromatic Green's function like this one here. And what a Green's function does is it gives the wave at some point RR in the receiving space that results from the point source at RS in the source space. Now, we want eigenproblems to get modes, but we need two eigenproblems because we have two different spaces. And these are not, therefore, just the usual eigenproblems of, say, a resonator in each volume. There is, however, a key mathematical trick we can use instead. With the coupling operator GSR between the spaces, for the source space, we can solve the eigenproblem for this different operator, the product of G dagger SR and GSR. The solutions to this eigenproblem give us an orthogonal set of source functions, so psi sj, in this Hilbert space HS. With the coupling operator GSR between the spaces, for the receiving space, we solve the different eigenproblem for the operator GSR G dagger SR. So we've swapped them around in order here. So we solve that to get an orthogonal set of wave functions phi rj that are in this other receiving Hilbert space HR. Note incidentally that these two problems have the same positive eigenvalues, the modulus squared of this number Sj. Now, when we have solved these two problems, we find that if we operate on one of these source eigenfunctions, psi sj, with the coupling operator GSR, we get Sj times the corresponding one of the receiving eigenfunctions, phi rj. So the source eigenfunction generates the corresponding eigenfunction as the wave in the receiving space, with this coupling amplitude Sj. Therefore, we have established the communication mode pairs of functions. Note that, by our definition of modes that we gave earlier on, each one of these two sets of functions, the source functions psi sj and the received wave functions phi rj, is a set of modes. The modes in one space are paired with those in the other. In practice, we only have to solve one of the two eigenproblems. We can deduce the solutions to the other one from, for example, GSR operating on psi sj gives us sj times phi rj. This mathematical process is actually the singular value decomposition of the operator GSR. For any linear operator we can think of, D, which we may think of as a matrix for convenience, at least as long as it is bounded, that is, it has a finite output for a finite input, we can perform the singular value decomposition. That is, we can write it in one of the following two equivalent forms. Here as a product of operators, which again we can think of as matrices, and here involving the functions. These are exactly the same, by the way. U and V here are unitary operators, that is, power-conserving operators if you like. D diagonal here is a diagonal operator with the elements Sm. And these are called the singular values. The psi m are the columns of U, and the phi m are the columns of V. Note that for the matrix elements of D, which we could call Gij, evaluated on any orthonormal basis sets we like, the sum of the modulus squared of these matrix elements is the same as the sum of the modulus squared of the singular values. And we can usefully write this as a sum rule S. This sum rule is important below for many reasons. It can be evaluated without solving the problem, and it gives a limit on the number and strength of connections. So, as an example, we're going to look at communicating between two surfaces. And we're going to presume arrays of small sources on one surface and arrays of small receivers or antennas on another. Here, for simplicity, we use scalar waves and point sources and receivers, though we don't have to use either of those restrictions. In the simulation, then, we simply use the Green's function to give the wave at each receiver from each source or antenna, and this gives a matrix connecting each source point to each receiver point. We then perform the singular value decomposition of that matrix to get our modes. We're going to take our surfaces as these areas here, a 16 wavelength square transmitter or source area and a 16 wavelength square receiving area. So we have two-dimensional arrays of sources and receivers that are emulating the situation for the communications modes with these two surfaces. So here we are plotting the field at the receiver. That's what's shown on this picture here. And these dots show the area corresponding to the area of all of these dots here. And we're going to look at this for each one of the possible communications modes. We'll go through all of these, but what is going to happen is that we're going to get a set of different communications modes, but you see that the coupling strengths are quite different for these modes. Note the finite number then of usable channels in this system. So here then, explicitly, is the same mode we've just been looking at. This particular one, not surprisingly, happens to correspond to the most strongly coupled mode. It takes about 12% of the total available coupling strength. Here is the second mode, rather similar coupling strength, and the third mode, which is just a symmetry variation on the second one. And here's the fourth one. It looks substantially different, but it's approximately the same strength of coupling. Here's the fifth, the sixth, another two similarly coupled modes, and then here is mode 9, here is mode 10, here is mode 11, here's mode 12. So we see that despite a large number of sources and receivers, we only have a smaller number of usable spatial channels. These channels are unique. We cannot get more orthogonal channels than this, given these surfaces and their separation. Now, so far I've shown you only examples for simple scalar fields, but it turns out that this approach extends to full vector fields. So for example, Here I'm showing the mode coupling between a line of sources and a line of receivers. We have a conventionally polarized mode as an example here, which is number 4. But this particular approach works out all the modes for all the polarizations. It even finds the modes corresponding to longitudinal polarization. Now that's not really a propagating mode, and in fact it decays very quickly. I've magnified the strength a bit over here. But we can see that it does in fact exist, and this model can find it. This approach we've been taking can handle full electromagnetic situations, and hence we start to lose the distinction here between optics and radio frequency antennas. This approach resolves paradoxes of numbers of channels. There has been a lot of confusion around the idea of orbital angular momentum modes. The channels we have calculated are the only orthogonal channels of the system. Adding in the concept of orbital angular momentum does not increase the number of channels. In fact, we can get exactly the same number of channels without invoking any orbital angular momentum. And this approach also works even as we go to large or even infinite numbers of sources and receivers. The approach is fully compatible with diffraction theory. In fact, it's actually a generalization of it. It introduces a sum rule that bounds all behavior. It works for continuous sources, as in optics, and more discrete sources, as we may often encounter with radio frequency antennas. We can take one further step, which is to look at a scattering problem. In this case, using the same mathematics, the relevant sets now become the orthogonal input modes that couple one by one to orthogonal scattered output modes. Now we're going to look at the idea of singular value decomposition again, but for the more general case of a scatterer, optical device or object, described by some operator D. So instead of just having free space in here, we are allowing some other device. One immediate consequence is that because we can perform the singular value decomposition of any linear operator, we have what we can call the mode converter basis sets of functions. These are, first of all, a set of orthogonal source functions, so functions psi s, that lead one by one to a set of corresponding orthogonal received waves, phi r here. In turn, that means that there is a set of orthogonal channels through any linear scatterer. And these sets of channels are simply given by these mode converter input and output function pairs. Note that these mode converter basis sets, as I'm calling them, become the optimum basis for the problem in one sense, and they include the source and receiver volumes in their definition. These functions, it turns out, also have basic physical significance, leading to new Kirchhoff thermal radiation laws in optics, a new modal version of Einstein's A and B coefficient argument that links spontaneous and stimulated emission and absorption, and also a new simpler quantization of the electromagnetic field. Now, none of these three fundamental points is of particular direct relevance to most of our applications in radio frequency electromagnetics, but the point is that these fundamental laws emerge specifically with these sets, and they suggest to us that this, in some important fundamental way, is the right way to describe waves. This idea has been developing in the literature since about 1998. It was picked up quite early in electromagnetic scattering, for example by Pieri and various others. It was picked up in wireless, in optical systems. There's been a lot of work in the intervening period, and I'll show you just one reference from 2019 that summarizes and extends all of this. So, in conclusion, I've tried to introduce what may be a different way of looking at electromagnetic waves from those that you're most used to. It's based on this two-volume idea, at least for source and receiving volumes, and the mathematical concept of singular value decomposition. This leads to modes being pairs of functions, one in the source and one in the receiving volumes, and I've argued that these give an economical and quite fundamental way of analyzing wave problems in optics and in electromagnetics generally. As I mentioned earlier, there's one major reference for this talk which summarizes everything I've said here and links to the other literature. You can also look at my webpage, and I'd like to acknowledge my funding from the Air Force Office of Scientific Research. Thank you for your attention.